In this video, we're going to go over section 2.1 out of your textbook, which is called Sets and Set Operations. This section is a little bit long, but we go through several examples. And so just as a warning, you may have to, take a break in the middle of the video if it gets to be a lot of information at one time. First, let's go through a couple of definitions of what a set is, and then we're also going to learn a definition that you're going to hear repeatedly throughout this chapter. All right, so a set is a collection of objects or things. Set notation is the notation that we use to describe sets, and we usually use those little curly braces that you can see on your keyboard. They're right next to the P button on your keyboard. The objects or the things that are in the set are called the elements of the set. So an element of a set is just a member of the set. So you're going to hear that word a lot through this chapter, the word element. So an element is just describing a member of the set. First, we're going to talk about well-defined sets. If there's a particular way of determining whether an item is an element of a set, then this set is called well-defined. So basically, if there is a set rule for determining whether an item is an element of a set, then that's well-defined. So let's go through some examples of sets that are well-defined and then some sets that aren't well-defined. So here we have an example. It says, which of the following sets are well-defined? First, we have the set of all movies directed by George Lucas. Then we have the set of all great rock and roll bands. And then the set of all possible two-person committees selected from a group of 5 people. Alright, so our first example here, the set of all movies directed by George Lucas. This is definitely a well-defined set. The movie is directed by George Lucas or it isn't. So there's a rule for determining whether or not a movie belongs to that set. So yes, this is a well-defined set. Next, we have the set of all great rock and roll bands. Now, this one is a little more foggy. Depending on what person you ask, they may have a different list of great rock and roll bands. So this is not well-defined. So there's no set rule for determining whether some rock and roll band is great or not. You could come up with a rule, and then if you stated the rule, you said the set of all great rock and roll bands, and my rule for if they're great is this. That could make it well-defined, but right now it's not well-defined. And then our last one, we have the set of all possible two-person committees selected from a group of 5 people. So you can imagine like you have 5 people in an office and 2 people have to be selected for a certain committee. This is a well-defined set. All you would have to do is just make out a list of all possible combinations of 2 people out of that group of 5. So yes, that is a well-defined set. Now, let's talk more about notation. I mentioned it earlier, but we need to go through it more in depth. A set is denoted by a capital letter, and we try to pick a meaningful letter if you can. So for example, if you're talking about the set of movies, you might call that set capital M. Or if you're talking about the set of numbers, you might call it N for numbers. Set notation is the method that we use to describe a set by listing each element inside of those little curly braces or set braces. You can see right here, those are the curly braces. And whenever you go to type in things, when you go to type in sets on your homework, you're going to want to make sure and look closely. Sometimes they already have the curly braces listed for you, so you don't need to put them in. And sometimes you may have to actually type them out. So just make sure and look before you start typing in your answer. Look and see if they already have the curly braces or not. And then very important here, this little bullet point is very important. It says when you're listing the elements of a set, each distinct element only needs to be listed once. All right, so for example, if you had a set and you were going to put the ages of everyone in the class, if I had 2 people that were 19, I only need to list 19 one time. All right, so you only list each distinct element one time. And also the order of the elements does not matter. Now that's just for this class. In another class, your professor may ask you to put the elements in a certain order if you're talking about numbers. But in this class, I don't care what order you put the numbers in. All right, a couple of more notation things we need to go over. Here we have this little symbol. It looks kind of like an E. It's right here. So this symbol stands for the phrase is an element of. And if you see that little E with a line through it, that stands for is not an element of. And then last one, people always forget this definition, so make sure you put a star beside it. This will definitely be something that you see on your quiz. It says the cardinal number of a set A is the number of elements that are in the set, and it's denoted by, here we have a little N, and then inside the parentheses says A. The way that I would read this is N of A. So N of A. Or I might just say the cardinal number of A. All right, so the cardinal number is just where you count up the number of elements that are in the set. All right, we're going to go over some examples of each of these little notation and symbol stuff. So let's look at an example. Here we have our second example. It says, let A be the ages of my students, and I just made up some numbers here. So A is the set 18, 21, 28, 39, and 51. So these are all ages. And you'll notice that they're in order from smallest to biggest, but that doesn't matter. I could have them listed in any order. It doesn't matter. All right, so first it says, what is the name of this set? All right, so the name of this set is A. And I chose A because it was the set of ages. So A for ages. So the name of this set is A. And then we have our next question. It says, is 21 an element of A? Is 21 an element of A? So yes, 21 is an element of A. You see it right there. So we say yes, 21 is an element of A. Next, we have a true or false question. This is a perfect example of something that you might have on the quiz. It says true or false. 45 is not an element of A. All right, let me read that again. True or false? 45 is not an element of A. So do you see the number 45 in this list? No. So this is true. 45 is not an element of the set A. Next, we have find the cardinal number of A. Find the cardinal number of A. So this again means count up the number of elements that are in A. So starting with 18, we have 1, 2, 3, 4, 5 elements. So the cardinal number of A is 5. Next, we have set builder notation. This is another type of set notation, and it's particularly useful when you're dealing with large sets. So for example, one example of a very large set of numbers is the set of all negative numbers. So I'm going to show you what set builder notation looks like. It says, let G be the set of all negative numbers. So you can tell if we were to have to write this out using our normal set notation, imagine if we had to go through every single negative number, like negative 0.01, negative 0.001. You know, we'd be here all day. So instead of writing out every individual number, we use set builder notation to give a description of the set. So it says a set builder description of the set G above is given here. This is set builder notation. And what I've done in the next little bit is I've written out how you would read this, because that's the hardest part. But usually this is something that people always catch on to pretty easy, and once you've seen it a couple of times, people tend to be able to catch on to this. So it says G is the set of all x's. So that little x there on the left, you read that as all x's such that x is less than 0 and x is an element of the real numbers. So R here stands for the real numbers. So all of the x's, x is a number here, all of the x's such that x is less than 0 and x is an element of the real numbers. So if you haven't learned about the set of real numbers recently, real numbers, this includes any number that you could possibly think of. This is whole numbers. It's the number 0. It's negative numbers. It's fractions, decimals, irrational numbers like the number pi, repeating decimals like 0.3333. So this is any number that you can think of. That's what a real number is. That's the definition of a real number. So this is just an example of set builder notation. We may have to use this throughout the semester. So I'll always try to remind you of how to read that if I present it to you and we haven't talked about it in a while. So here we have some examples, or another example, and it just wants us to describe the set. So here we have our first set. It says this is all of the x's such that x is greater than 0 and x is an element of the real numbers. What are some elements that would belong in this set? So just to remind you, the elements of this set have to be greater than 0 and they have to be real numbers. So basically you could pick any number here as long as it's not 0 and it's not negative. Alright, so I just picked a couple of numbers here. I picked 1, I picked 0.5, which is the same thing as a half, picked 3/4, and then 1400. You could pick just any number that was greater than 0, and that is a real number. So these were just some numbers that I thought of. Our next set is not a set of numbers, which is totally fine. You can use set builder notation to describe any type of set. It doesn't have to be a set of numbers. So this set is the set of persons such that the person is a living former U.S. president. So once again, try to think of some elements that would belong in this set. Here are some examples that I came up with. George W. Bush, Barack Obama, Jimmy Carter. I'm sure there's a lot more that you could think of. These were just ones off the top of my head. These are living former U.S. presidents. All right, and then our last set that we're asked to describe says it's the set of women. So it's the set of women such that the woman is a former U.S. president. All right, so what are some elements that would belong in this set? There are no elements in this set as of yet. There have been no U.S. presidents that were women. So this is an example of what we call the empty set. So when a set has no elements that belong to it, that is called the empty set. All right, so once again, a definition here, any set that has no elements is called the empty set. And then just a little fact for you here, since the empty set has no elements, its cardinal number is 0. All right, and then I should have included here a little line. This symbol right here is the symbol that we use for the empty set. All right, so it's a 0 or an O with a diagonal line through it. Make sure you don't do a straight up and down line. It's got to be diagonal. If you do a straight up and down line, that's a different symbol. All right, so that symbol represents the empty set. So instead of writing out the words the empty set, we'll just use that symbol instead. And then it has just another little fact here that sometimes people get confused. It says the set, that's just the number 0. So let's say this is your set and it only contains this one element and it's the number 0. This set is not empty because it has an element and the element is the number 0. So, for example, the cardinal number of that set, the number of elements that are in that set would be 1. So any set, even if it just has one element, even if that number is the number 0, that still is not empty. Now we're moving on to universal sets and subsets. The universal set is denoted by U, and it's the set of all possible elements of any set that's used in the problem. Now, the universal set is not one standardized set. It's not always the same. It changes for each problem. So usually if you're looking at a problem on the homework, they'll tell you, hey, the universal set is this set of numbers. All right, so just pay attention to the problem, and they'll usually, if you need to use the universal set, they'll tell you what the universal set is. So that's the set of all possible elements of any set used in the problem. Now, it says when every element of one set is also a member of another set, we say that that first set is a subset of the second set. Okay, so let me say that again. If you have a set and every element of that set is also a member of another set, we say that that first set is a subset of the second. And this is the symbol that we use for subset. It says notation, A is a subset of B, is denoted by A, and then we have this little symbol right here that means is a subset of B. So A is a subset of B. I'm going to go through an example using subsets and universal sets. It says let U be the universal set where U is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I've picked the set A to be 2, 4, 6, 8, 10. Alright, so notice that every element that is in A, also is in the set U. Alright, so A is called a subset of U since every element of A is also an element of the set U. And so using the symbols we just learned, we would write A is a subset of U. So A is a subset of the universal set. Now we have sort of similar notation to when we were looking at that element of and not an element of. So it says if A contains an element that's not in B, then A is not a subset of B. And that's denoted by this symbol here, which you would read as A is not a subset of B. So here we have another example. I've picked the same universal set as last time. And it says let A be the set 0, 1, 2, 3. So notice that the set A contains the number 0, and 0 is not in the set U. Okay, so A is not a subset of U since A contains an element that is not in U. So A is not a subset of U. So using our symbols that we just learned, we would write A is not a subset of U. Here we have a Venn diagram where I am expressing the relationship A is a subset of B. So you can see everything that's in A is contained within the set B. So here we would say, you can see right here, A is a subset of B. And they're both a subset of the universal set. So that's this big set out here. You can see the U. So both of those sets are a member of the universal set, or a subset of the universal set. All right, we have two more things to learn, and then we will be done with this section. Now we need to learn about the intersection of sets. The intersection of a set A and B, denoted by A intersect B. All right, so this little symbol right here, that little upside down U, we read that as intersect. So A intersect B. This is, it has this kind of complicated set builder notation formula. It says it's all of the x's such that x is an element of A and x is an element of B. So basically, it consists of those elements that are common to both sets. Right? So anything they have in common, that's going to be in the intersection. So pretty simple. You just look at the sets, you look and see what they have in common, and that is the intersection. Let's look at an example. Suppose we have sets A and B, where A is the set Aquaman, Batman, Flash, Superman, and Wonder Woman, and then B is the set Batman, Blue Beetle, Booster Gold, Fire, and Flash. Alright, so let's find the intersection of these two sets. To find the intersection, again, you're going to look and see what they have in common. The first thing that I noticed that they have in common is Batman. And let's see, what else do they have in common? They also have Flash in common. Alright, so those are the only two elements that they have in common. So the intersection of A and B, A intersect B, is Batman and Flash. And notice that that forms its own little set, so that still goes in the little curly braces. Here we have a Venn diagram illustrating the intersection of two sets. And if you have a Venn diagram, the shaded region that's in the middle, that's a part of both sets A and B, that represents the intersection. Alright, now building off of the intersection of two sets, we have something called mutually exclusive. Whenever two sets have nothing in common, so that is they have no overlap, these types of sets are called mutually exclusive. Another name for these types of sets is disjoint. Disjoint. So for example, consider an ordinary deck of playing cards. Let D be the set of cards that are diamonds, and let S be the set of cards that are spades. Now, if you think about a deck of cards, you know, what do the cards look like in the deck? It's pretty straightforward. Pretty easy to see that these two sets are going to have nothing in common. A card cannot be a diamond and a spade at the same time. So these sets are mutually exclusive. No card can be both a diamond and a spade at the same time. So this is a really easy example of a mutually exclusive set. Here we have a Venn diagram illustrating mutually exclusive sets. Just notice that they have no overlap, so they don't touch at all. They have no elements in common. Alright, and once again, I've written down for you here, sometimes your book will call mutually exclusive sets disjoint sets. Those mean the same thing. So you could say two sets are mutually exclusive or disjoint if they have no elements in common. That is, if the intersection is equal to, do y'all remember this symbol? The intersection is equal to the empty set. So that symbol represents the empty set. So that basically they have no elements in common, so their intersection is equal to the empty set. The last thing we have to learn, and then we'll be done, I think, the union of sets. The union of two sets is a new set formed by joining those two sets together. So really, the union is really easy to find. All you're going to do is you're going to take everything from both sets and put them into one gigantic set. And the only thing you'll have to remember is just not to repeat any elements. So for example, if 2 is in both sets, you only have to write 2 one time. Here's the formal definition of the union. And this is the symbol that we use for the union. This one's easy to remember because union starts with U, and its little symbol also looks like a U. So it says the union of a set A and B, denoted by A union B, is, says all of the x's, I'm right here reading, it's all of the x's such that x is an element of A or x is an element of B. It says the union of A and B consists of all elements that are in either A or in B or in both. That is, all of the elements that are in at least one of the sets. Let's look at an example. I like this example a lot more than the Batman example that we did before, just because this is what your examples are going to look like on the homework. So it says, given the sets, A is the set 1, 2, 3, and B is the set 2, 4, 6, find the following. So part A, we have the intersection of A and B, and then in part B, we have the union of A and B. All right, the intersection, sorry that popped up really fast. If you notice, the only thing they have in common here is the element 2. That's the intersection, that's the things they have in common. All right, so the only thing they have in common is 2. All right, so let's slow down before we jump to the next answer. Now let's look at the union. The union of A and B, like I told you before, all you're going to do is you're going to take the two sets, A and B, you're going to put them together and make one big set. And just don't repeat any elements. So you're going to start with A, or you could start with B, it doesn't matter. Like I said, the order that you write these in doesn't matter. So we'll have 1, 2, 3, and then we'll go over to B, and we've already got 2, so we don't need to write that again. Then we'll also add 4 and 6. All right, so 1, 2, 3, 4, and 6. And I've got these in order from smallest to biggest. Like I said before, it does not matter. You can put these in any order. It does not have to be in order from smallest to biggest. Oh, I'm sorry. We have one more thing to learn. All right, complement of a set. The complement of a set, denoted by A with a little apostrophe, this is read as A prime or the complement of A. I use A prime, so that's what I will call it. This is going to be all of the elements that are in the universal set and not in A. So let me read that again. The complement of a set consists of all elements that are in the universal set but not in the given set. Now this sounds kind of complicated. I'm going to show you a really easy way to do it. Alright, I'm going to show you a really easy and quick way to find the complement. Here we have an example. It says, given that the universal set is 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A looks like it's the odd numbers, 1, 3, 5, 7, 9. So again, the universal set is 1 to 9, and then A is the odd numbers from 1 to 9. Find A complement. Alright, so what that definition said, it said it's everything that's in the universal set that's not in A. Alright, so what you're going to do, really simple, you're just going to go through one by one and mark off each one of these numbers that are in A. Mark off every one of those from the universal set. Alright, so let's start doing that. We marked off 1, mark off 3, 5, 7, and 9. The stuff that's left over is the complement of A. Alright, so you can see it's the even numbers 2, 4, 6, and 8. Alright, so A complement or A prime is 2, 4, 6, 8. Alright, that's everything for this section. I know it was very long. If you stuck out the whole way, I really appreciate it. Let me know if you need any help with the homework, and I'll see you in the next video.